करना पड़ेगा. Now it is.
So, good evening to all of you. Of Honorable Dean, I welcome all of you. Platform provided by where alumni share their knowledge gained after the PhD, which is in turn beneficial for our students. So today we have with us Dr. Vikas Kumar, who has done his PhD in 2017 on the synthesis of Polix cloning back and nuclear recycling work. And after that, he has gained lot of experience in that path. So we are going to listen from his mouth. So because the mic is to you, you have 45 minutes. Please try to wind up your talk in 45 minutes.
Sir, thank you, sir, and thank you for the introduction. Myself, Vikas Kumar. And I am from 52nd batch of training school in chemistry discipline. And I joined VRC in 2009, and I joined there in hydrometallurgy section. I was a chemist, and there is a well-known chemist in our section that time called Dr. Jain Sharma. He is also called as solvent man. Dr. Basu has given him this name to him, and I joined directly with him. And that time, a molecule was very called calyx crown. Basically, this molecule is used for extracting. It's highly selective cesium from high-level liquid waste solution. Yeah, that time. So that time, that project, in that project, I entered and I started working on this particular molecule, slowly gaining the experience. Earlier, my master's was in physical chemistry, but I started my journey from organic chemistry, this thing. And after that, after 1 year of completion, suddenly one day Sharma sir came and told that because this molecule is very difficult, and I had listened very bad thing from other person that this molecule will not make, you cannot make because this is very difficult. So I told sir, I will take this challenge and I will do PhD in this only. He was very happy, and after that I applied for the PhD in the same topic, whatever it is there, synthesis, characterization, solvent extraction, and theoretical studies of calyx crown based ligand for cesium extraction from acidic media. This was my topic, and this was unchanged throughout my PhD. And I worked very hard in that field, experience, and you will be surprised that this which we make was used in our backend around that time. The cesium pencil to cesium, and finally the cesium nitrate was converted into cesium oxide, and then it was vitrified in glass and used as cesium pencil. We also applied to it that time. And in between, I will share for my younger colleagues that I will share some experience, you can say bad experience also. Structure of calyx, you see there are around four these, and almost this particular tosylate also requires 3 steps, total 8 step synthesis. This is quite difficult actually. If you start with the material, this phenol, if you take 100 kg, then you will end up with around less than 5 kg. Yield is very poor in this case. Then slowly we synthesized, and what happened, this particular molecule, when we synthesized, this comes under supramolecular category. And when I synthesized it, I went for analysis and looked. Its NMR was matching, its elemental analyzer was matching, but this mass which you do not have because we are having GCMS only. So I take this molecule for analysis at IIT SAFE. There I did LCMS, liquid chromatography mass spectrometry. The molecular ion peak was missing. Though everything was okay, but molecular ion peak was not there. It was showing some extra M plus 18, M plus 40, M plus 23, etc. So we thought we are not ended with the same molecule which we actually thought of. So again, after 3-4 months of again, we tried again. I synthesized this particular molecule again. Again, the same issue came. The LCMS was showing not the molecular ion peak; it was showing extra peaks, but molecular ion peak was missing. So I was very shocked that यार इतना काम करते करते हो गया अभी तक हो नहीं रहा है तो अभी क्या करें? So we then Sharma sir told that you first do extensive literature. So I found one paper in which LCMS with this type of calyx crown, there is always molecular ion peak will not come. It will always associated with either with water, either with potassium, either with sodium and or ammonium ion. These are present in our aqueous in whatever dilute this mineral DM water you use, this will come. So from there I learned a lesson that I thought that I will share with my younger colleagues that before going to actual conclusion, you should always use a good literature, extensive literature study should be done. Not only synthesis part, but on analysis part also. And this particular molecule also worked well around 100 gram we made, and this was given to this WIP, and there they did mixer settle studies, and they told that this is okay and this will work. And one more experience I would like to share. If you see, note when we were sitting and I was discussing with my technical advisor, he was telling that because you know the cesium and strontium both are very culprit for high level liquid waste because these contain around 1/3 of radioactivity and 1/3 of heat. So why not we make a molecule which will be selective for cesium and strontium both? Means we can take this cesium and strontium in one shot. Then we had experience that strontium can uptake by dichloroamide type of unit, and this cesium we had already very selective ligand for this. Then we tried. I synthesized this particular molecule, and this particular molecule took around 1 year. This is very difficult when compared to the other molecule. After synthesis, it was analyzed. The molecule is okay. Everything was fine. And when we taken for solvent extraction study of cesium and strontium, it took only cesium, but not in good amount, and strontium 0. Means whatever synthesis, whatever the time we invested, we just failed. Means the इतना मेहनत करने के बाद zero result. लेकिन molecule was new, so it was published. So I was not much worried. But sir was not very happy. My technical advisor, he told that because you do one thing, you first go and learn this theoretical calculation, mainly DF. That time DK Maiti sir was there in HBNI only. That time he was shifted, and there was 20 classes of theoretical, and I attended all those and started the working small molecule gamma software. This is open version software. Slowly I learned many things. Means basic I had cleared, but for this particular molecule, these are big molecules, so these will not be useful, not be used in GAMES software. GAMES is actually not taking ECP, effective core potential type of thing. So then Maiti sir suggested that because there is a person called Musharraf Ali sir, you go there, I will speak to him, he will help you because he is having a license of the turbomol software, which is very good for a large molecule. Then I went to Musharraf Ali sir. Then he also guided. He gave me the license. I think he is the one of most helpful person in BRC in my point of view. Otherwise, I don't know. So he helped me, and from that onwards, we started. First, we do calculation whether it will take or not. We see, we compare with our data, old data. Then we end up that this molecule should not be made or should be made. So this was our target. So by doing so, so many publications, etc., and finally this particular molecule also went in plant scale, where I think this earlier molecule is already being used, is actively used. And you might be aware of that this cesium pencil, I think that time 100 pencil they had supplied to breed from this my molecule only. And after completing my PhD, actually that time I was young also, and we North Indian always prefer to go to our native place or transfer mil jaye to acha hai, because GCNP was there. It was new institute and I did my PhD, so I thought that I will take some PhD student do R&D there. So sir told that you first complete this particular work, then only I will allow you. Then I completed all the work. Then okay, you can go. Is I was transferred. After there actually GCNEP whatever not actually applied, but somehow I have to come back because R&D culture was not established there, and that particular was not supposed to for R&D also that time. Now I do not know what is the status. After that, when I came back after 3 years, uh, I was given some other assignment like this titanium making, like from hydrometallurgy to now pyrometry. This is 180-degree shift. Means from synthesis carbon hydrogen, now I have to shift on this titanium making technology. Titanium, you are aware of wonderful material, uh, so many good properties like it is carbon steel, strength is double, almost double. So this is for used for our departmental application. So King sir was that time our group director. He told me, because this is very challenging work, I think you will do good in this work, this only. Then sir, I told sir, okay sir, no issue, I will join. And this is the basic flow sheet how titanium is made. Titanium is made basically TiO2. If you see, this is very simple. TiO carbon plus chlorine gives TiO4, and therefore this migration to get titanium. This looks very simple. In our country, we don't have yet full-fledged titanium plant. There is one private plant, KMML Kerala, which is making, but the TICL for technology is US DuPont only. And so in this way, I entered in this particular project. And if you see this titanium TiO2, it is not exactly the TiO2. It is ilmenite to slag. Then slag is now feedstock. Then it will be converted into TiCl4 plus FeCl3, etc. So many things will be there. Then it will be distilled. After that, this TiCl4 will be reduced with magnesium. Online magnesium Cl2 should be removed. Means it contains almost, it is मतलब सबका बाप है टाइटेनियम का टेक्नोलॉजी अगर आपने बना के दिया है, तो अगर ये मतलब मेरे को जब इतना पता है कि अगर जिसने टाइटेनियम कर लिया है वो किसी भी मेटल में काम कर सकता है. After spending so many years, 5 years, finally we are given at this technology, and there is a plant which is in RETTMP, Rare Earth and Titanium Theme Park, Bhopal. It is there now. 50 kg they are producing. So from this, if you see this magnesium is, and then even magnesium we do not make. Even by electrolysis, we, in our country, we do not try making with salt electrolysis. And we had it. Same in the same if you see system in our prep also. So I told the Dr. Avasti sir, that time I a very good teacher also. He introduced me in this project, like first starting with the furnace. He told how the furnace is made, like all the furnace, resistance furnace, induction furnace, up to arc melting, high temperature, 2500-degree type of furnaces. He just give the hint, and we are making this small little experiment we do by its own without spending so much time on the so much time and money on the research. So then he and sir, I told sir, why this magnesium, calcium we cannot make. He told that okay, you want to make, go and uh, try. I told sir, okay. And then we both spent around 2 years by using some design, high temperature process, everything was applied, and finally we ended up with a good process as well as design which can produce 1 kg of high purity calcium, which is already we demonstrated in our hall 4. It is there. And from that calcium part which you had given and uh, given another work which you can say as a side product which appeared as a for the reduction of rare earths. Now this my actual the work was started, sir, which I supposed to present. Before that, I just present so that our young colleagues can get. Uh, so about rare earth, how the methods, how will you reduce the rare earth oxide roadmap for vacuum reduction distillation, development of reduction decondition based on thermodynamic calculation, experimental validation, and conclusion. This is the layout. Now, what are the rare earths? Now, you can see this from lanthanum to lutetium. These are called rare earth. These are rare earth because these are rare and having so good application. Even countries are in war with these rare earth critical minerals. And this can property matching with the rare earth. If you see this particular car, around if you see 8 to 9 kg of rare earth is used in this particular hybrid car nowadays. So you can see that so huge requirement of rare earth is there. And basically, these rare earths are distributed in two parts, lighter and rare. Heavier from lanthanum to Nd, it will lanthanum to samarium, you can say lighter, and up to above these are heavier. Our country is reaching lighter, but heavier are not there in our this sand. And one beauty is that where the lighter will be found, there will be no trace of heavier. Where the heavier will be found, there will be no lighter. This is the beauty of this rare earth. And why I am telling this volatile, this thing, rare earth volatile, because rare earth metal, they should not be volatile. This is the reason why I am saying that these are volatile, because if you see the boiling point, ytterbium is around 1100 degrees Celsius. And means these are small, you can see the deep are there in this thing, these four rare earth. So that's why I am telling it as a volatile. And if you see, if you want to make suppose lanthanum, cerium, Pr, Nd, the method is basically either fused salt electrolysis, like lanthanum chloride will be there, and there will be a fused salt, and at cathode you will get lanthanum, at anode you will get chlorine. We had already a plant at RETMP for lanthanum, cerium also, and say PR and ND can be done. But another method for getting rare earth is make their fluoride and fluoride and treat with calcium and magnesium. That which have earlier in our plan. So then NdF3 plus calcium gives Nd. This is the method, so that means only fluoride can be reduced with getting this thing. But there are issue with this four metal: samarium, europium, thulium, and ytterbium. These four cannot be obtained by the simple molten salt electrolysis से, or you can say this either fluoride बना के use कर लो, fluoride बनाया, chloride बनाया, calcium से treat करो, वो नहीं बनेगा, because this is because this is having the reason for this low boiling point is basically these are divalent and trivalent, two state exist, and one try to get complete this either complete full shell or partial full F shell. So, and this is because this is the factor that's contributes. It is having +2 and +3 oxygen state. Once you do for molten salt electrolysis of this samarium, ytterbium, you will never end up with product, because once suppose samarium 3 is reduced to samarium 2, but samarium 2 again means there will be a mismatch of current density. How much current density you have to take, because you are planning for samarium 3, but you are now this is samarium 2 and samarium 2 is stable, then it will not further reduce that electrode. So this, and why those fluoride route is not there? Fluoride, because once you use fluoride like samarium fluoride plus calcium, this reaction is so highly exothermic, there will be like explosion type of things can be happen. So what is the plan that how you can obtain this then? These four materials, these four typical materials. So basically, let us slowly let us develop a concept. Like if you want to reduce a metal oxide, what you will do? Either first, like iron, if you see whether it can be reduced with carbon, whether it can be reduced with hydrogen, and this is the aluminum diagram. You might be aware of that. This basically this gives the relative stability of oxides with temperature. Means whoever is lying lower is more stable, and whoever is lying is least stable oxide. So if you see rare earth almost lies below. So these cannot be reduced by this carbon. Carbon cannot reduce. If you see hydrogen, hydrogen will never reduce because this is almost parallel line. And if you see, you can say that carbon line is going down. Once at a temperature of 2000 degree, this will definitely intersect. Then why carbon cannot be used? Because this calculation we did, and there was one more competing reaction like this rare earth carbide formation with CO evolution. Then these two reaction will be is there. If you try to reduce it with carbon, then if you see that partial pressure of CO, because this is a gas and partial pressure of CO will decide the free energy of reaction. If you try to reduce, it will end up with samarium cobalt because partial pressure for this particular reaction is and with samarium cobalt, not with aluminum. You can see from the graph. These are the calculation based on CP that from names and things. So this is hydrogen and reaction. Now, what should be the magnesium? Magnesium is also saying if you, but what about here? Yes, calcium definitely you can say that it is once you reduce of oxygen. No, this is because once you go on reducing, and oxide and the last thing so this is the way, and this I already told that how what is the methodology, how you can say how to reduce rare earth, either by using molten salt electrolysis or by using fluoride or chloride reduction with Mg alkali metals or alkali or alkaline metals. But these four metal cannot be used because highly exothermic formation of dihalide, and dihalide are more stable, they cannot be reduced. And molten salt because multiple oxygen state. Once a material is having multiple oxygen state, that will always be avoided in molten salt electrolysis. So, but this there should be a technique that by which this can be produced. There is technique called reduction distillation. So let us make a concept for this reduction distillation. If you see this rare, if you try to let us try to do it with aluminum. Aluminum, you can see aluminum cannot reduce, na? But it can reduce. Let us do it with some different calculation. If you see at standard condition means at 1 atmosphere and at any temperature. If you see the delta G0 for this particular reaction is positive, so it is not feasible. So, but at non-standard condition, delta GR should be is equal to delta G naught plus RT ln K, and this K active K was written in terms of activity, and finally activity is written in terms of partial pressure. And this partial pressure in terms of let us then at equilibrium condition when delta GR is equal to 0, then this equation reduces to this 4, and this PRE was calculated, and this PRE was then put in this number 5, then this PRE, which this PRE basically, let us say PRE for this reaction comes 10 to the power minus 3 millibar, means at 10 to the power minus 3 millibar delta GR is equal to it is 0, but delta G naught is also equal to 0, means it is in equilibrium. So once you apply a vacuum better than 10 to the power minus 3, this delta G will be more negative. This is the funda basically, which we applied, means at high temperature and using the vacuum. And these are the plots. These are in left side there is ytterbium and europium, and in the right side there is samarium and thulium. This is the log scale, log PRE, and these are the these plotted. These are only theoretical calculations. These are plotted, and once you see that at around 800 Kelvin, if you see this particular this black one, europium can be can easily be at 800 it cannot be done. But if you go at around 1200 degrees Celsius, if you see the partial pressure is coming under rotary range. Rotary range means 10 to the power minus 3, basically vacuum. If new students are there, then 10 to the power minus 3 means rotary vacuum, 10 to the power minus 4 to minus 5. You can say DP vacuum, diffusion pump vacuum, then thermomolecular TMP, and then titanium sublimation pump type of vacuum, high vacuum. So if you see at so to Kelvin, yes, rotary can reduce uh, this degrees Celsius. And if you if you go on reducing this ytterbium 1200 degrees Celsius, there is requirement of diffusion pump, DP vacuum. No rotary will work. And of course, for increasing the kinetics, you have to raise temperature little bit higher. And in the right side, if you see the reaction with aluminum, if you see, it requires very large temperature even to get in the DP region for samarium. So aluminum cannot reduce. Aluminum requires very high temperature for its reduction of this particular samarium oxide. And for this thulium, this is less. This is even more. And similarly, on the same scale, this why silicon cannot be used. Silicon, if you see silicon, this is straightway upward. Means you will end up with you have to take vacuum around TMP, more than TMP. If you can titanium sublimation pump type of vacuum, even at around 1300 degree Kelvin. तो ये इसमें नहीं होगा. इन दोनों सिलिकॉन इज स्ट्रेट वे रिजेक्टेड. सिलिकॉन कैन नॉट बी यूज्ड. एंड if you do it by reduction by using lanthanum metal. Lanthanum is also also a rare earth, and it is also used for reduction of samarium oxide and ytterbium oxide, etc. If you go and plot this particular plot, if you see for this europium, if you see, even less than rotary, means watering pump even can work if you use this lanthanum for this europium. And for this ytterbium, rotary vacuum is good enough for working at 800 Kelvin. And similarly, if you go for samarium and thulium, where the temperature and pressure conditions are very severe, in this case, if you see at around 1300, 1200 Kelvin, if you see there is DP, you can use DP vacuum to get the samarium or thulium out of it. So this way, this concept was developed, that how much temperature and how much vacuum you require for reducing a particular metal. And this is our setup. This particular setup looks very clumsy because this furnace, which I already told that Dr. Avasthi sir has given us the funda to how to make furnaces. So then we make furnace like कुछ भी अपना बना के हम लोग तुरंत यूज कर लेते हैं उसको. जैसे आप बनाया है, मतलब 2 दिन में बनाया, यूज किया, काम कर रहे. तो दिस इज ए वेरी, you can say, homemade furnace. We can it can go around up to 1200 degree Celsius. And this is vacuum trolley, and this is chiller unit, and you can see the vacuum reading at 10 to the power minus 4 minus, and this is the temperature around 1140 degrees Celsius. And this is the how ytterbium metal deposits. If you see, these are the condenser, and this is the YB pellet which we have made. And this YB pellet, basically YB is used in our department for certain pharmaceutical applications. And this is the pellet we had supplied to BTTG group for certain laser and radio pharmaceutical application. And these are the method how to make, like first mix lanthanum and oxide in appropriate ratio. Heat up to whatever the temperature comes from calculation, and apply the this vacuum whatever it is coming, and mechanically strip from condenser and vacuum seal product and in our atmosphere. And this is our backbone of our R&D operation. Like he is Mr. Tiwari, and she is Archana Prajapat, and ये पाटिल है हमारा सबसे अच्छा आदमी, मतलब सबसे यंग है ये. और ये पे है अपना श्याम जी. ये both Shyam ji and Tiwari ji are above 50, but they are working like they are just joined the department. They are very hardworking person. And the Archana is our XRD expert. She do XRD and XRF etc. for our work. I thank all of them if they are listening. and they are in mission mode. Like they do, this work is also in the process. This is actually a big setup for the same kind of this thing purpose. And finally, thank you all. You have any doubt, then you can ask. Crucible is only, if you can say, it is basically why crucible matter, because you are condensing now. Iron will not come.
No, but you must be
Yeah, I know.
condensing in some container, no?
I know, but it is not yet published, so I should not really supposed to tell. But it is SS based only, stainless steel, high nickel type.
What is the purity of the metal you are obtaining after reduction?
So, madam, once you are condensing a material in a cold space, so the impurity will come very less. Means from this boundaries, the impurity will be very small. But once you scratch it, it will be around 100% pure because it is distilled. No, it is high vacuum. Mhm. It is not there, but for increasing the kinetics, you have to apply either go for high temperature or high vacuum.
So this is the best by distillation or there are other?
Actually, this is not purification. Actually, this is a process for reduction distillation. Once you are taking oxygen from it and condensing it somewhere where you predetermined space where you want to get the metal. Actually, that depends on boiling point. If you, the boiling point is if you in this case if you use if you use like calcium, if you want to use, or aluminum you want to use. Aluminum is having boiling point around 25 degrees Celsius, 2500 degrees Celsius, and lanthanum is much higher. So impurity from lanthanum will be very I think negligible, you can say. But if you use like calcium is having boiling point 1500 here, that will impurity will come.
Same series there are.
No, actually lanthanum is pure because lanthanum we have plenty, because already we have plant. It is almost giving 99.9% pure lanthanum. If you are saying mish metal of thing, no, we are not taking mish metal. We are using only pure lanthanum. Purity around 39 pure it will be there.
So what? I have one question. What was the content of this your reducing agents like lanthanum or aluminium in that metal that you produced?
No, it is not there. I am taking only these are basically I developed a concept that aluminum can be used.
No,
This
you
is
used. I'm
one.
telling
Wait,
you-
sir. Wait, sir. You are asking what is the content. Content, no content is there because lanthanum is having very high boiling point compared to this
No,
ytterbium.
but have you analyzed? It will be in some ppm, no? So that I wanted to know what was the content, the level
Whatever,
of impurity
sir,
content.
the
It will
material
definitely
came-
be there.
What
We have produced some metal from calciothermic reduction. Residual calcium content is there. So
Sir,
that's why I wanted
sir,
to
sir,
know what is the
calciothermic it
residual
will be
content.
there. Calciothermic it will definitely be there if you do by calciothermic.
But whether you have
Because
analyzed
boiling
for
point is-
lanthanum and aluminium, that I wanted to
XRF
say.
shows 100%.
No, XRF is okay. XRF is not for
No, no.
ppm impurities. No.
You have to go some low level.
मतलब you have to do some by this chemical volumetric analysis, then you will get that impurity in ppm level. So
Wait, sir. This ytterbium oxide, whatever we received, actually it is very costly and we do not have resources for ytterbium oxide. And this came from a BTTG group. They are, I think they has procured, and once we made, there was no complaint.
For
that
comparison, I'm not
and-
complaining. I just for my
and
sake,
for-
knowledge sake, I wanted to know that from calciothermic radiation, this is the
Yes.
impurity residual impurity level. From
Yes.
aluminium, what is the residual impurity level? And from lanthanum, we are producing. Then what is the residual content of the metal? That for if you're not analyzed, that is
No,
okay.
no,
But
sir.
if you analyze, you can share.
No, the ytterbium, whatever you had made, it is very costly, and we don't want to spoil any metal. So whatever the metal came, and we did XRD small like It is.
But
It was,
once you can
it-
check now, once
no,
you
no,
can check,
no,
then
no.
we'll have
It is like it is ductile. All the characteristic, like if you have some oxygen impurity, it will not be flattened.
Yeah.
But in this case, this is like a this very easily like aluminium. You can beat it, you can flat it, and XRD, etc. Everything was we did. We were sure there was no issue, and the party which we had this not party, our group, they had not complained that because we don't want to spoil any little material. Why?
Many
Okay,
applications
okay.
require very high purity. How you check with the high purity? For that we have to do some analysis.
No, no. If yes, that should be done, but we don't want to spoil
and it requires only milligram quantity of your metal sample for this analysis.
Yes, it will
But
require.
once
But
you can do for your own sake, you can claim that this is the level of impurities that we have.
Mhm.
Just
Actually,
can I
sir,
interrupt? Can I interrupt? Can I
Sir,
interrupt?
Less.
No, means my take is this debate, otherwise this will keep on going. So what now he says, if I understood Vikas correctly, he says that because of the availability of the material, which was at disposal, he could not do that. But you are making a valid point that somebody can extend it further and they can do it. Okay. No, true. True.
It is
That's
required in microgram scale actually. It is
Right.
required in microgram scale. Microgram per week.
sometimes time constraint availability they have not.
no, sir. Actually, there was no issue with the analysis. We can do. But the things was because this was in
Questioning your product. It is only my
no,
suggestion that
sir,
you can take.
there is no issue. I will give it to you once I will speak to that. We will ask some product and we will give it to you if you want to do analysis. But
we can discuss.
something कुछ लोग होता है ना, देखते पहचान लिया ना, अरे मेरा बच्चा है, मुझे पता है, वो
Because-
होता है,
because-
ऐसा नहीं है कि पता चलता है कि हाँ ये हुआ. Madam, I know, but this setup is not only for YB. We are making so many things out of it,
Any question
and that
from
are
online also? Somebody is there?
99.99% pure. But I don't want to disclose that also.
Online, you can check. Sunny, just see if somebody is there online. Somebody has joined. Yeah. Somebody is there online. Any questions from the online participants? Okay, because today there was some light issue was there. Anyway, this is recorded on the YouTube and nahi hai. Where is nahi? Satpati sir, you have any questions?
Welcome, sir.
You told that that by calciothermic reduction, as it is a very exothermic, you have avoided. Why? Exothermic means this is a very feasible reaction. So why you have avoided?
But once you locally, it is locally it is producing very high heat. So and boiling point is less. So definitely this will boils out and
that
puncture the
control,
retorter.
that controlling mechanism is there also. Anyway, another question is that why you have not converted to fluoride or chloride and then by reaction with the calcium that can be a
No.
product also.
This your question you had asked first question, that was fluoride with calcium. This is highly exothermic. Not direct SMO2O3 plus calcium. It is not exothermic. This SMF3 plus calcium. This is highly exothermic. This means fluoride with calcium or magnesium. This is exothermic.
Okay, next is the that in Bhopal you have given that theme park, you have given the technology transfer with respect to magnesium chloride, separation of magnesium and fluorine or chlorine.
Magnesium and
That
Sir, actually,
molten salt electrolyzer
sir,
has
I
been
know,
established. There is a very interesting subject. You know, this is a burning point as of now because in NFC magnesium fluoride that stock is huge basically. That is a present time requirement. If it can be splitted out, then that chlorine can be utilized by the NFC as such, and then for the production for the zirconium, that magnesium is required. This is required, and if it is successful, I am telling you for the UED also magnesium chloride we are having, so we can go ahead for that purpose. So we are basically badly waiting for this technology.
Sir, in magnesium chloride, if you say in magnesium chloride had worked, basically magnesium chloride is hexahydrate. first before molten salt electrolysis, if you go, you have to remove this hexahydrate.
Which
6
one?
water molecule.
Inside.
Magnesium chloride, 6 H2O is there.
Hmm.
Water of hydration. And before molten salt electrolysis, you have to remove the 6 H2O also.
That is also possible.
But when you try just like NaCl, if you go on giving the temperature at around 600, 700, water will go. But in this case, it will not go. 700
that,
degree.
200, that we do not know. That TG, DTG, that we have to do it, then accordingly we have to
No,
get
sir.
that.
I want to tell you some. If you go on doing like NaCl, you end up with MgO, not anhydrous MgCl2. This is finding, not my finding. This is literature one only.
That
And
is okay. I am talking about chloride, magnesium chloride straight away.
Huh.
Whether that electrolyzer has given the sufficient product, because this is a hot burn cake basically. This is requirement for the time now, and that so many people are waiting for this technology. I am telling you, this is as good as this is a achievement. That is a Viksit
Yes.
Bharat program.
yes, that we definitely try, sir.
You
But
just see.
once it should come to our boss.
Okay. Okay. Can I ask something, Vikas?
Yes, please.
Okay. So first of all, Dr. Vikas, I must thank you for giving a talk on such a important topic, because if you look at the rare earth are the hot topic from ground level to the highest level. See, even Greenland is also then being discussed many times in this context. Okay, so that you can say, and the wage on a debate is going on. Okay, the questions you can do further means when people are asking, okay, to find out the ppm level, this means something is there.
Yeah, I know.
So we must appreciate that thing, but at the same time I have very few trivial questions. Okay, the first question is basically that I just want to understand, maybe I have skipped. So you made a statement that the lighter rare earths and heavier rare earths, they are mutually exclusive.
Mhm.
Is there any chemistry behind that also, or
There is chemistry, but right now, sir, I do not know. But
Ionic ready,
many.
Ionic
ionic
ready.
radii? Okay, okay, that is the reason.
Yes, ionic ready from lanthanum to samarium is close enough. Then later on again close enough.
Okay. No, but what I wanted to understand is that that makes it that okay, only one type of land means this. They will be at one place. Lighter one will you find in one type of ore,
Yes, sir.
and the heavier one in the second type of ore.
Yes.
That makes it.
Yes.
That is the reason. Okay. That was just for my out of my curiosity. And other question is, if you go that to that your Allingham diagram, na, you showed that. I just want to understand. So Sir has also asked,
Sure,
calcium
sure.
will do. That Allingham diagram you just show. Yes, this one. 8th slide. If you look at, see again, Chanasi, you nicely explained that this carbon reduction is not possible.
Mhm.
Okay, but with respect to calcium, you told.
Sir, actually this line is shifted.
Okay.
Initially it is lying down, and then it is going up. This kind of thing.
Okay. And then you told that okay, because if you want to do at normal this atmospheric pressure, that you will have to heat up to very high temperature. That is the
Yeah,
reason.
for
That's
this
why you are
carbon, if you go on reducing, it will take intersect around 20 to 100 degrees Celsius.
Okay.
This will require very high temperature.
High temperature. But by vacuum distillation, you are going for the reduction in temperature. That is helping
yes,
you.
by reducing
That is the
temperature.
reason. Okay. Okay. And that okay, you nicely explained that this white cannot be obtained by electrolysis +2 to +3 valency. So there is no other way. This will lead to maybe some change in this happens simultaneously. Or see, for example, what I understand is as a fundamental that the voltage you are going to apply, because current density will depend upon that. Okay, so this voltage regulation is difficult there, or what are the issues in that
No, sir.
technology?
Actually, if you do, we actually tried also, but we are never get this product because this was containing like some type of, neither it was pure metal, neither it was pure oxide. And this was our means we did actually, and then later on we found that yes, it cannot be done because of this reason only, like 3 to 2, and then 2 is stable, then again 3 will come into 2, and once you apply high voltage, then 2 will come. So means this equilibrium type of thing will be existed, and the current density that we have to fix actually first. That this was current density I used to play, but that is varying with your this thing. potential also. So you will never get products, sir.
And finally, when you are going for this rotary vacuum or DP, what?
Yes.
Industrial scale, which one is more feasible from your point of view?
Sir, industrial scale, actually, if roots and rotary is there, then it is okay.
Okay. And that is feasible.
And you want to prepare, you want to go for some higher temperature, any kind of material if is required.
Okay. So that's again related to what question he asked. What is the material of the crucible and all those things? So that will come into picture. Anyway, thank you. That was all from me, and I'm really thankful for giving such a wonderful talk. Definitely, John, it must have. Yeah, madam.
Yes.
Because this all the things are so just one person that someone was doing some PhD or something which industry
Madam, put mic on. Put mic on, madam.
No,
This is the-
okay. Which industry and which they will get some
Now, recently, Government of India actually had tried to give this beach sand type of material. Like earlier, they was having some limit that this much radioactivity should not be there. But now they has increased the limit. Now private vendor will be coming, and now private vendor in titanium as well as in rare earth, everybody they will come. And nowadays, I think some this thing negotiations are also on the way. So private parties will definitely come in this rare earth part.
okay. And also for internship and those things, is a possibility in some industry they can.
Once you start working on this type of work now, then definitely if a person, if I would be a PhD student, then I will definitely open my own company with startup.
The startup is one another one other aspect. And the person is doing in some field this research, there is a possibility that they can go to internship in some industry so that afterwards they can learn something from industry. Is it possible?
That means you have to explore.
I will give the answer. In the sand mineral, it is having, along with the other minerals, he has started from the retail. So, along with other minerals, it is having monazite also. Subsequent quantity and sufficiently good quantity. Monazite means rare earth and thorium and iridium. So that monazite business, no private player is allowed as of now after this bill also. Okay, Shanti bill. Thereafter also it is not allowed. Okay, so whatever mineral except monazite you can do it. Monazite means that rare earth also. Okay, now it is coming to the Ambadunga. That mineral maybe having little bit of thorium or negligible amount of thorium, and then correct or not?
Yes.
Rare earth content is heavier, but lighter is rare. So that plant basically, that's why that Gujarat government now they have started already that mineral separation process. Correct, na? So there is a scope in that area.
Otherwise, it is
Wherever otherwise for the beach and mineral till now you can do the all business, but except monazite, you can do all mineral, you can separate it out, and you can do the business. But monazite that is to be handed over to the government. So monazite means it is having the rare earth. So rare earth business, filal, with respect to correct or not? With respect to beach and mineral, it is not open up.
that is okay, but it is in this at least with this experience, they may go to some other field and get some.
The other like that I told now that Gujarat and other thing, where that inland mines are there, inland mines, maybe open cast type of things. There you can go and do it, provided there is no monazite. Monazite means okay. So
Yeah.
so people should think in that aspect. Other mineral I can do the business, but except this rare earth and other, that is restricted.
But now, sir, government I think planning is something that is.
You can do it. See, I know that Kerala government also some that unit is there. No? They are also getting that beach and mineral, but they are stocking pile that A also, that monazite. They are not processing. Except monazite, that will be handed over to IREL once or after some time. Except that monazite, then remaining business they are doing. Kerala government. Rutile, other mineral also.
Thank
And
you very much.
zircon is there. Zircon is there.
Zircon is also having EVNIum.
Huh?
55% EVNIum.
No, zircon. No, zircon. That zirconium plant is not a radioactive plant. It is not having uranium. It may be contaminated with the monazite. Then only it is. Otherwise.
Okay, sir. So, madam, you want to say something? No. Okay. Okay. If there are no more questions, let us thank for your comments. Yeah, you can ask.
For this regular production of SMCO magnet, this method is only being used, or
No. Actually, that is separate task. Samarium oxide and cobalt both are mixed, and with calciothermy only they are doing. Basically, that is called reduction diffusion. Once
Okay.
samarium oxide is reduced, this cobalt penetrates and enters in the samarium matrix.
in one SMFE some magnet?
That is NDFeB magnet.
No, that is separate. But samarium, some other compound is also there. SM2CO17. For that,
SM2CO5, SM2CO7, there are 2, 3.
for that also.
That is byproduct. That is actually produced in SMCO5 only.
Okay.
Thank you, sir.
Okay, sir. If there are no more questions, let us first and foremost thank the speaker for giving today's talk. Okay, and at the same time, I thank Dr. Satpathy and his colleagues my other colleagues from BRC, my associate dean Dipanvita madam, Madhumita madam, and assistant dean Pramjit and Bhavita Tiwari, and of course the IT team for organizing this seminar. And we hope that we will continue this in future also. We'll have many more talks, and maybe some of the issues you can discuss later on also. Okay,
Sir, we are in the same group.
right? I know. See, your presence itself that shows that not only it was. I can see that it was a two-way traffic. Vikas also must have learned many things, I'm sure. Okay, from the questions, because the questions give you something to think over. It is both way, and that the purpose is being served.
Yes.
Thank you very much. Thank you, everybody. Thank you, sir.